All right, with that, I am going to pass over to Josh. Josh, thank you so much for talking to us.
Can I just chime in and one little clarification for Pete's introduction to Josh? So Josh, Pete said he just finished at Penn, but I should clarify, he just finished his undergraduate degree and joint master's degree at Penn. We're actually keeping him on to be a PhD student, so he'll start as a PhD in the fall with me and Mark Yatzkar as the supervisors.
Yeah, it's great to be here. So I'm going to give a talk on how to do interpretable text classification using text bottleneck models. So as Chris mentioned, I'm an incoming PhD student at the University of Pennsylvania, where I'll be co-advised by both Chris and Mark Yatzker. And the project that I'll be presenting today is done with mentorship from their PhD students, Veronica Liu, Yu Yang, Ian Dugan, and also with mentorship from Mark and Chris. And I also note here that UA is on this call. Hello, UA.
Hello. Good luck.
Yeah, so in this talk, I'll give an overview for how to construct these text bottleneck models. And the work we're currently presenting is in submission for COLM 2024, so be on the lookout for that. So the main motivating question we have for this paper is, how can we check if our models are working as intended? Well, in the domain of NLP, we have multiple ways of evaluating model reasoning. You have things like looking at attention scores, looking at sample-based explanations. And in these newer generative models, what we can do is prompt the model to generate its chain of reasoning before every answer. But we note that a lot of these methods of looking at model reasoning can run into certain issues. For example, I mentioned attention scores. Looking at attention scores can be a lot like reading tea leaves. In this example, where you have this span of text being considered for the quality of the coffee, you can see that the words aroma, that the words mouthfeel, short finish, they're important, but you don't really quite know how the model is using them. You know that they're weighed very highly, but you don't exactly know any of the global principles for why these words are important and how they're being weighed against every other word in the context. And then for the other end, for things like chain of thought reasoning, a lot of the chain of thought reasoning isn't necessarily guaranteed to be faithful. The model can say one thing about how it arrives at a certain conclusion, but you don't actually know what's going under the hood in terms of whether that reasoning is the actual reason for why it arrives at a certain answer. So going over these potential issues, I highlight two of them. One issue is with faithfulness. A lot of interpretability methods are essentially done post hoc without access to the model's internal structure. So it provides a reasoning that kind of tells you which things are important, but there's not necessarily any guarantee in terms of why these things are important or if they're being used in the manner that you think they are. And on another level, a lot of interpretability issues suffer from issues with understandability, because ideally, in a good explanation, you would understand the high-level principles for how a model is using the evidence that it's looking at to arrive at the conclusion. A lot of methods only essentially provide local explanations. It tells you why this instance is classified this way, why that instance is classified this way, and which things are important in each explanation. But overall, you don't have any global explanations or higher level principles to understand how the model is working through each singular problem. So how do we try to address these issues? Well, what if we try to provide additional structure? And in the work that I'll be presenting today, we're extending off of a piece of work that's been published 2 years ago called Language in a Bottle, which essentially applies this concept bottleneck idea to the field of machine vision. So the idea behind it is we want to move away from this whole paradigm where you have an end-to-end network. You give it an input, for example, an image of a bird, and you want to identify the label for what kind of bird it is. And in an end-to-end network, you just provide an image and you get this label, black-throated sparrow, but you don't really know why the model assigned it the label of black-throated sparrow. Under a concept bottleneck model, the main idea is, rather than trying to directly predict that, okay, this image is a black sparrow, what if you try to predict intermediate concepts first? So you try to predict the fact that, okay, it has a certain nape color, it has a certain bill shape, it has a certain head pattern, and then taking all of these things into consideration, what is the label? And the main benefit of having a concept bottleneck is that there's much more interactivity because of the interpretability. Because let's say you're a human practitioner and you notice that, hey, the nape color isn't actually gray, it's more black, or the bill shape is not actually conical, it's more like rounded. What you will be able to do is you'll be able to step in and correct the nape color to black, the bill shape to rounded, and arrive at a better label, essentially. The main challenge of implementing this approach is that it's pretty human intensive, because as you can imagine, if you try to build this whole thing out yourself, right, how would you do it? You would need to get a human expert, an expert birder, and they'll say that, okay, in your model, you'll need to have a concept for nape color, bill shape, head pattern, and then you'll get a bunch of crowd workers, you'll get 100 of them, and they'll look at hundreds of pictures, and then for each of the concepts that you designed, they'll try to label them one by one. So as you can imagine, this will be pretty labor intensive and potentially underperform end-to-end models, because you'll only be able to focus on the concepts that exist within that bottleneck. So in this previous work, in the language in the bottle, how did they generate these concepts? So how they generated these concepts is by first prompting a large language model, GPT-3, to describe things like, okay, describe what the black-throated sparrow looks like. And it generates this long completion that contains a lot of descriptors for what the black-throated sparrow looks like. And then what you can do with these descriptors is transform them into concepts. So in this example, they have multiple sentences from GPT-3 describing what the black-throated sparrow looks like. And then they post-process these into snippets that essentially take the form of, they transform these into concepts that essentially take the form of these phrase concepts. So the concepts in this paper, language in the bottle, take the form of these phrases: small bird with a black head and throat, white body with brown streaks on its back. And then what they do with these phrase level concepts is that they sort them on visual similarity to gather the phrases that are most similar to the images that you want to label. And then they further process them to only include concepts that have high discriminability with respect to the images that you want to label. And what you end up with at the end of this whole process is that you're able to arrive at these predictions that have some level of explanation. In the top left image, for example, for the badger, the reason why the model labeled this image as a badger is because of the concepts: short legs, long body, black and white striped fur, and the coat is very shaggy. So we can see that this works pretty well in the domain of image classification. Now, how do we transfer these ideas into the field of NLP? Well, going back again to the main challenges really come in two. First, we have to be able to figure out what concepts to include in the bottleneck. One running example that I'll keep mentioning in this talk is the example of restaurant review classification. Given a restaurant review, what is its rating on a 1 to 5 star scale? So if you want to create a concept bottleneck for the domain of restaurant classification, you'll need to get some expert, and then the expert will tell you that, okay, you have to focus on ambiance, service quality, food quality, so on and so forth. And then after coming up with those concepts, the hard part really is trying to measure them in zero shot, because since we're essentially measuring or generating these concepts using a large language model, you're not necessarily guaranteed that there's going to be a nice labeled restaurant dataset with all of the ambiance, food quality, service quality of all the restaurants already labeled. So we have to generate these concepts and then measure them essentially in zero shot without any background dataset to help ground those measurements. So with all of those challenges noted, how do we implement text bottleneck models using large language models? So in our whole system, there's 3 main modules that we need to look at. We have the generation module, which generates the concepts. We have the measurement module, which measures those concepts in zero shot. And then we have the prediction module, which takes into consideration all of the concept scores that we measured to arrive at the final prediction. So going into the first part of this module, concept generation, how do we do that? Before that, though, something that we note is that, or something that we want to first discuss is, how do we structure a concept under our work? If you can remember in the example I've shown before in the language in the bottle paper, the phrases mainly took the form of phrases, so they weren't very structured. But in this work, we expanded the idea of a concept to have more structure. So for each concept, you now have an associated name, an associated concept description, and very importantly, for the zero-shot measurement, each concept comes with its own concept question with its own possible responses. And for each of the responses, you have a short description describing, okay, what would it take for a certain text to fall under each of these labels? And then since at the end, we want to combine all of these concept scores to generate the prediction, we map each of the potential responses into a numerical score. So in the backend, when the LLM that we use is generating these concepts, we essentially structure it as a JSON. So let's now discuss how we prompt an LLM to generate these concepts. So we have three main parts in the prompt for generating these concepts. First, we demonstrate the task by showing it some examples of concepts on different domains. Next, we show the LLM some examples from the dataset. So we say that, okay, this is what a concept looks like. You're generating concepts for the restaurant domain. These are what the texts look like. And then at the end, we provide a list of concepts that the system has already generated to just avoid issues with repetition. So let's go into each of these steps one by one and what they look like in the prompt. So in the first part of the concept generation part, you have the instruction. And in this part, we essentially tell the model that you will be given a text data set with accompanying labels, and your task will be to generate the concepts. And a concept is defined by a name, a description, a question, a response set. And for each response, you have a guide for what it means for a given text to fall under that label. And after that, we provide some examples of concepts on different datasets. So in our few-shot example, we essentially only give the model examples of 3 different concepts. We have a concept for assigning toxicity scores to social media texts, a concept for evaluating the sentiment of product reviews, and then a concept for doing scam detection for emails. So this is what the model has in context when it tries to generate another concept that follows this template. So after showing the model the definition of a concept and some examples of concepts, we then provide examples about the data set that it's trying to generate concepts for. So we say that your job is to generate concepts for this or that data set. This is what the data set contains. These are what the labels mean. And these are some examples of texts with different labels. And what we essentially do here is that we prompt the model to pay attention to the different labels such that it picks up on differences that exist between texts that have different labels. And that's how we kind of steer it to generate concepts that are more on the discriminative level.
What
And
question? How do you pick the examples that you show?
I will talk more about that later.
Okay.
But yeah. And then at the end, after showing them the examples for the data set, we essentially have this recap, just summarizing the task that it needs to do. So we remind it that it's generating concepts for this data set. And we just have some additional notes saying that avoid making overly broad concepts. Try to make them more objective. Just some additional steering parts at the end. So this is what an abridged version of the whole prompt looks like. So in the blue part, you have the description for what the task is. In the green part, you have the information on what dataset it's trying to generate concepts for. In the orange part, you have examples of the concepts that the system has previously generated. And in the pink part, you have what the system arrives at, what the system generates in the form of a JSON. So that's the entire process for concept generation. It's very long and convoluted, but it essentially sets us up to make everything else easier, especially for the next part, concept measurement. So when you're trying to imagine what the system essentially does when it's doing concept measurement, it's essentially trying to answer questions about text in a zero-shot manner. And you can essentially imagine it taking the shoes of a crowd worker on MTurk, where it's shown a piece of restaurant text, for example, and it's given this multiple choice question about quality of service. And its task is essentially to determine which of these potential responses to quality of service best matches the description within the text. So when we're performing this measurement step, we can essentially use any prompting method that we like, since an LLM is answering these questions. So we can use anything from chain of thought reasoning. We can use multiple chain of thought reasonings and do self-consistency. And here's another idea that I quite like. If a concept is quite difficult to measure, we can also maybe put another TBM under it to also have interpretability in terms of how we answer that question. So in terms of what we actually implement in our paper, what we do is first make the model extract relevant snippets over the text and make the model reason over those extracted snippets. So what does that look like? So first, in our concept measurement prompt, you have this instruction, which essentially says your task is that you will be given a text, and then you will be given potential buckets for the snippets in the text to fall under. So in the example here, if the task of the model is to measure something like good build quality, and the potential responses for good build quality can be high, low, uncertain, what it does is that it's supposed to go over the text, and then for each of the potential responses, extract snippets that might correspond to each of those potential responses. So for example, here for the concept of good build quality, for the high snippets, it extracts really easy to use, and it is also very durable. But one interesting thing to note here is that really easy to use is not exactly related to good build quality. And note that this is in the exact this is in the exact prompt that we use for concept measurement. So something that we intentionally do in the prompt is that we show an example of where it makes a mistake in the snippet extraction. And in the chain of thought, we show that, okay, there's two snippets for high, but only one is related to durability. So in this example for the prompt, we essentially demonstrate to the model that sometimes there are mistakes in snippet extraction that you can correct in the chain of thought reasoning so that it can ignore pieces of information that are essentially irrelevant.
Josh, what is the role of the snippets? Because all you really care about is the answer.
Mm-hmm. So one advantage of the snippet-based extraction is that it can also help in the interpretability of the model. And I can show you an example of what that looks like in a later slide.
Okay.
So yeah, putting everything together, how do we combine these concept scores into a final prediction? So note that what the system does is that it's able to provide integer scores for each concept being measured. And what we do with these concept scores is that we train a linear head over it. So if we're doing a regression task, we can train a linear regression over them. If we're doing a classification task, we can train a logistic regression model over them to predict the label given the concept scores. And looking at what inference looks like now under this system, you can see here that on the left, you have the input restaurant review. And in the middle, you have what the concept bottleneck looks like. So in the concept bottleneck for restaurant reviews, you have customer recommendation, value for money, romantic atmosphere again, restaurant variety, all existing as concepts. And the nice thing about this, since we're using a linear model, is that you can essentially read off the importances of each concept based on the weights. So in this example here, you can see that customer recommendation has a weight of 0.4545, which tells us that it's a very important concept, whereas noise level barely has any weight in the system at all. So in this way, you can see that the system provides a lot of global interpretability, because just by reading off of the weights, you can already tell the main things that the model pays attention to. And on the second level, you also have local interpretability, and this mostly comes from how you set up the measurement module as I've described before. And this is what I was talking about when I said that the snippet level extraction can come in handy, because in the customer recommendation part here, you can see that in the step down view that you have had a great brunch on Mother's Day is highlighted in red because it was highlighted as a positive snippet for a good customer recommendation, whereas the snippet of the ambience wasn't what I expected is highlighted in blue because it was extracted as a negative snippet against the customer recommendation. So you can tell here, based on how the system is set up, that you have potentially a lot of global and local interpretability for how the model works. So
Just a quick question. Would this be able to handle sort of global features of the review? Like, let's say it's like dripping with sarcasm. So like if you read the whole thing, you realize the whole thing is sarcastic. And if you take any snippet out of context, it will look positive, but they actually meant it negatively if you read the whole sense of the review. I don't know if this can sort of handle that.
I guess one weird thing about the fact that we're using large language models for measurement is that it can potentially handle that, but it can also not potentially handle that. Because one thing that the system can do is that it can also have a concept for sarcasm, which allows us to pick up on that. But since also we're using a large language model for measurement, in the atmosphere measurement, for example, if it notices that it's describing the atmosphere, but in a very sarcastic manner, it's quite likely, since it's using an LLM, that it's going to be able to pick up that it's describing the atmosphere in a sarcastic manner and thus reflect that in the negative score for atmosphere.
And Josh, let me just mention, there is the risk of kind of cycles here, like just with customer recommend, does this review recommend the restaurants? Yes, if the customer recommendation feature is high. So that's slightly tautologous. But I think you're going to mention that later, right?
Yeah, that's another potential issue in the system, and that's an issue that we call leakage. Because one thing that can go wrong in the system is that the system is essentially trying to provide overall a restaurant review rating. But if one of your concepts is restaurant review rating quality, then that essentially makes the whole bottleneck kind of pointless, because it is essentially push all of the weights in the linear head towards that one concept, which kind of harms the interpretability of the system overall.
I wonder if there's a way of kind of detecting and then masking out those kind of tautologous concepts.
Yeah. That's something that we tried to do in the work for the paper. And yeah, in terms of some additional notes for how the whole system works overall, I made gestures towards this earlier, but the way the system works is that we generate concepts iteratively. So at the start, we have 0 concepts, and then we generate one concept and then generate another. And then each time we generate another additional concept, we have the choice of whether or not we want to add it to the bottleneck. And the way that we decide whether we want to add a concept to the bottleneck or not is fairly simple. We have essentially on the training set, if we add another additional concept, we test to see if the addition of that concept improves the performance by some threshold. We discard concepts that don't improve the model beyond a certain threshold. And this helps us get rid of concepts that are non-discriminative. So for example, if you have a concept like uses the word the a lot, then that will be something that will be filtered out by the model because it's not very discriminative in terms of trying to predict the model. And another advantage of this is that it kind of prevents us from having duplicate concepts, because if you have concepts that are being measured in a very similar way compared to the other concepts, then that wouldn't provide any additional information and would thus be filtered out.
And one danger with that is that, like, if the first concept you create is like a very broad concept, like in the worst case it's like overall review rating, then every subsequent more fine-grained context will be like a subset of that, and you might not pick it up. So maybe there's a sort of a more pragmatic, like, oh, let's generate a set of concepts to start with or something like that, so you can get maybe some diversity in the granularity of the concept or something like that.
Yeah, that's true. And that's also another reason why we want to provide overly leaky concepts, because leaky concepts essentially jam up the learning of the model, in addition to harming the overall interpretability. And there was a question earlier about how we decide which examples to load into the example for concept generation. And in terms of how we decide which concepts to load in and which examples we want to load in, we essentially load in examples from areas in the concept space with high error. So for example, you have a concept space here with 2 existing concepts, one concept for service quality, another concept for food quality. But then when you look at the concept space that generates, you have a lot of concepts in the middle which don't necessarily have any information about service or food quality. And ideally, we'd want to sample from those areas where they also have high concepts to encourage the model to learn more diverse concepts to improve performance on examples where we're making a lot of mistakes. So yeah, now that I've described overall how the system works, how it generates concepts, how it measures concepts, and then how it generates predictions based off of those concepts, let's look at the results for how this works on a bunch of different data sets. So first, looking at the end-to-end performance, we're going to look at the end-to-end performance in two buckets. One is sentiment-based domains, and another is non-sentiment domains. So let's look at the performance on the sentiment domain. And here we look at its performance on classification tasks like Rotten Tomatoes, Amazon reviews, Poem Sentiment, as well as regression tasks on Kebab, the open table reviews that are the running example in this talk, as well as Yelp reviews and hate speech scoring. And we compare against things like fine-tuning BERT, fine-tuning DeBERTa, fine-tuning GPT 3.5. And we also compare against GPT-4 when we're doing 10-shot. And one interesting note about the performance of the model is that it's fairly competitive. You can see here that the text bottleneck model, when we're looking at classification tasks, that it beats quite. There's a nice gap between the text bottleneck model and fine-tuning BERT and DeBERTa. And it's also able to somewhat match fine-tuning GPT 3.5 for classification tasks. And then looking at the right for the scores on regression tasks, we can see that the mean squared error of the model is also slightly on the level of fine-tuning GPT 3.5, and it's much lower than fine-tuning BERT, fine-tuning DeBERTa, as well as doing two-shot on GPT-4. So overall, we can see that the performance of the model on sentiment domains is quite good. But then the story changes when we look at its performance on non-sentiment domains, and this includes things like SNLI, AG News, patent domain classification, scientific paper citation intent, fake news detection, as well as partisanship detection in news. So you can see that the performance of the model is now well below the performance of doing Q-shot on GPT-4, which is quite interesting because the TBM itself, the results that we've been showing so far, we're using GPT-4 here for concept generation and for concept measurement. So it's quite interesting to see that it already underperforms Q-shot on GPT-4. But one way to look at this is that Q-shot on GPT-4 is not necessarily as interpretable as the text bottleneck model. But at the same time, we can already see that it's able to beat the performance of fine-tuning BERT and fine-tuning DeBERTa, while at the same time maintaining that level of interpretability.
Josh, there's a question from Shivanshu.
Yep.
Shivanshu, go ahead.
So I was wondering, how do you select the 10 shots for GPT-4?
We're essentially doing random selection over all of the examples for GPT-4. So we randomly sample examples and then weigh it so that you have even representation across all the different labels.
Have you tried other approaches? Because in context learning is extremely the performance can go up a lot if you select with respect to every test input. Given that your fine-tuned models are getting to train on a proper pool, a fairer comparison might be to actually select from that same pool, more dynamically select for every test instance. And then you might see a lot more different results.
Yeah. We essentially did the most basic thing we could here, which is, when we do the 10-shot, we make sure that all the labels are represented and we randomly sample so that we don't run into any errors where we happen to have a bad example at the start. So the random sampling hopefully avoids some of those issues.
Also, if you're doing random, do you also do multiple seeds?
Come again?
Or do you also do multiple seeds for each instance? Or is it just once?
Each time it performs inference, it randomly samples from the texts.
But do you do it multiple times for every instance or just once?
Just once for every instance. So each time we perform inference on another example, if it's a binary classification example, if it's a binary classification problem, for example, we randomly sample 5 negative texts and randomly sample 5 positive texts and load those into context.
Okay, got it. Thank you.
So yeah, that's the overall performance on the model on these different tasks. So we can say that, yeah, it's fairly competitive for sentiment, not so competitive on non-sentiment tasks, although we are able to beat the baseline set by fine-tuning DeBERTa. So now let's look at the quality of the concepts being generated by the model. We mentioned earlier that there could be some issues here, particularly with leaking concepts. So let's look at the actual prevalence of these concepts across all of the different tasks that we looked at. So we examined concept generation on 5 different tasks. So we look at Yelp, Kebab, Amazon reviews, fake news, poem, sentiment, and hate speech. And we look at 5 potential issues that could exist with the concept generation. One issue is with redundancy. Are we generating a concept that already covers the ground that another concept has generated before? Another is relevance. Are we generating concepts that are relevant to the task at hand? And third, and quite importantly, is leakage. Are we generating concepts that already encroach on the original task that we're trying to label? And then next, we also measure objectivity and difficulty. Essentially, are these questions that we're generating reasonable questions for an LLM to try and answer? And overall, we find that we don't have much issues with relevance, objectivity, and difficulty, but we do run into issues with redundancy and leakage, with redundancy being the larger issue.
How do you score these things? Is this by hand?
Yeah. So we had 3 authors on the paper go through each of the concepts and then just annotate if this potential concept is problematic on this domain or not.
I mean, in a way, your algorithm should guarantee you don't have redundancy. So maybe what appears redundant is not actually redundant.
Mm-hmm. What we looked at in terms of redundancy is issues that exist in this example, where in the bottleneck for this restaurant quality review, you have romantic atmosphere and atmosphere both being generated as concepts. And the potential issue here in terms of interpretation is that, yeah, it would be very weird to interpret these concepts because they're essentially about the same thing, but they're weighed differently. So for the purposes of interpretability, ideally, we want to have the concepts as atomic and separate as possible so that it's easier to interpret the effect of each. So this is, yeah, the results of what we looked at when we looked at concept generation. And then next, we also examined the performance of the module for concept measurement. And the way that we examined concept measurement is that we looked at the questions that the LLM was generating in terms of the concepts. And then we had crowd workers or students from Chris's really big AI class look through each of the problems being generated by the LLMs and essentially stepping into the shoes of the measurement module and answering the multiple choice questions as if they were the system. So because of how difficult and intensive this is, we ran this analysis on 2 different datasets. One is the Kebab restaurant review datasets that we've been using as a running example. And another one is the problem of fake news detection. So first, looking at the Kebab restaurant review dataset. So again, this restaurant review dataset contains texts that are about restaurant reviews, and they're labeled on a 1 to 5 star scale, depending on how much someone liked the restaurant. So let's look at some examples of the concepts being generated by the system and the questions associated with them. So looking at the concepts, you see that a lot of them are fairly reasonable, and you'd expect that an LLM would be fairly good at answering them. So for example, you have ambience quality. What's the customer's perception of the restaurant? Is it positive or negative? Food quality, is it being described as high, average, or low? So we look at the performance of the model in relation to human annotators and answering these multiple choice questions. And what we find is that the model that we're using, which is GPT-4 for concept measurement, is fairly good. you can see that the performance is quite high for a good number of concepts. You can see, in fact, that about 7 concepts are being measured with an accuracy of 90% or higher, which is quite encouraging, with about only 4 concepts having an accuracy less than 75%. So you can see here that a vast majority of concepts are being measured with high accuracy. And you can imagine that some of the concepts being measured with low accuracy are presumably from concepts that have a lot of degrees of variation. We would count it as a mistake in this example if you measured the restaurant food quality as good rather than excellent. So in these simple questions in this domain, we can see that using the LLM for concept measurement is quite accurate. But when we look at harder domains such as fake news detection, where the task is trying to figure out whether a piece of news is real or fake, that the problem becomes more challenging. Because in this example, let's look at some of the concepts that we're trying to measure. You have things like genuine source citation. So does the text contain citations from identifiable and trustworthy sources? And as a human, you can already tell that some of this starts to become kind of subjective, because what does it mean for a source to be trustworthy or identifiable? And looking at concept number 4 here, fact checking, you should be feeling kind of worried here, because the question that we're asking the model is, are the facts mentioned in the text verifiable? And the potential responses could be, yeah, all of them are verifiable, some of them are verifiable, and none of them are verifiable. So looking at this concept, you can already tell that maybe the model wouldn't be quite so good at this. And when we look at the performance, when you compare it to its agreement with human annotators, you can see that it does have quite an impact, because you can see that almost half of the concept are being measured with an accuracy of less than 60%. And if you compare this with the histogram earlier of the accuracies, you can see that there's quite a significant leftward skew in terms of how accurate the concepts are, in terms of how well they're being measured.
Do you also have intra-annotator agreements on this? And would they look similar?
So something that we note is that when we did these annotations, we had 3 annotators rating each example, and we simply took the majority agreement. I don't have the exact figures, but we also did tend to notice more inter-annotator disagreement with regards to fake news. So that kind of tells you that there's maybe 2 problems here with the concepts being generated. One is that not only is it impossible for the LLM to answer some of these because of the capabilities of the LLM, and on the second level, even if the LLM was very good, a lot of the questions that it was generating was quite subjective, to the point that even some human annotators were disagreeing about some of the proper labels. So yeah, after going over all of the results from all of our different analyses, let's go back to our original question, which is, how can we check if our models are working as intended? Well, under the TBM structure, when you compare it to these end-to-end neural networks, you can see that there's a lot of different ways you can start to answer these questions. If you're using a TBM, there are many ways to check if your model is working as intended. One thing you can do is examine the concepts. Do the concepts make sense? Do we see that the concepts are related to the task we're trying to measure? Do the concepts leak the label? Are the concepts impossible for LLMs to answer? And then after examining the concepts, we can look at the measurements. Are the concepts being measured correctly? Do they agree with human annotators? And then one thing you can also do is examine the concept weights. In the example of restaurant reviews, do we really expect that having a customer explicitly have a recommendation, is that more important than having a restaurant that is not noisy? So there are many ways to verify if your model is working before you put it into deployment. And even after you put it into deployment, if your practitioner notices that its measurement for a certain concept is wrong, it can step into the model, correct its measurement on a given concept, and then arrive at a better prediction, essentially. So with all of those nice features mentioned, let me mention some additional other nice features and applications about this text bottleneck model. One nice feature about these text bottleneck models is that you have interpretable learning curves. Because as we mentioned before, since we're generating each concept iteratively, you can measure the impact of each additional concept on the performance on the test set. So for example, here in the Yelp review learning curve, you can see that, okay, you have positive aspects mentioned being a concept, then the mean squared error decreases when you have mention of poor service appearing, and then it sort of glides down with the addition of all of these other concepts before it drops again suddenly with the addition of customer recommendation as a concept. So while the model is training, you can sort of tell, okay, this is what it's learning compared to if you just have a black box model and you only really know what it was able to learn after you finish running the training set and then do your analyses on them. Under the TBM, it's kind of like you're doing the analysis as you train the model, which is really nice. And then one nice application of these text bottleneck models is you can essentially automate your data exploration. So an example that I have here is from the ethics dataset, which contains examples of texts for different ethical questions, which are labeled based on whether or not the situation was ethical or not. So I encourage the students to eat paint is an unethical scenario label as 1. I put the pie in the oven for 35 minutes is an ethical scenario, so it has a label of 0. And then you can see here in the report that the TBM generates that you have all of these different concepts like disregard for personal dignity, neglect of duty, deception or misguidance. And along with each concept, you can also analyze each of the weights. So you start to pick up on things like, okay, deception or misguidance is the concept that the model that has the most highest weight in this bottleneck. So it's fairly important compared to something like violation of rules, which only has a weight of 0.13. And then in addition to looking at each of these concepts and each of their weights, you can also step in to see what each of these concepts actually mean. So for presence of harm, for example, you can say that, okay, this is what presence of harm means. This is the potential responses for presence of harm. So you can imagine that if you have a new data set and you don't know exactly what's going on with that data set, you can just chuck it into the TBM and get a nice summary of all the different concepts in that domain or in that problem that help explain the variances of the examples in the data set. Then finally, another nice application you can do is comparing text distributions, because one thing you can do is fit one TBM on one data set. So for example, you can train a TBM on Rotten Tomatoes. It generates the lists of concepts for you along with their associated weights. You can then take the same concepts you got from Rotten Tomatoes, and then instead of doing another classification over Rotten Tomatoes reviews, you can look at reviews on Letterboxd. And then once you fit the linear head on the Letterboxd reviews, one thing you can do is compare the weights such that you can now tell, okay, in the Letterboxd model, you can see that you have a weight of 4 on cinematography, whereas in Rotten Tomatoes, you only have a weight of 2. And then the conclusion you can arrive there, is that, Letterboxd places much more weight on cinematography compared to Rotten Tomatoes, and Rotten Tomatoes cares much more about acting quality. So with all of those things said, we can now conclude with the conclusion of text bottleneck models are very promising. The additional structure makes it easier to analyze model behavior, and the modular nature makes a lot of extensions possible, because you can note some of the decisions that we've made in this approach. One decision that we made is that in the final step, when we're generating a prediction, that we generate the prediction using a linear head. But one thing that does is that it sort of restricts the kind of complexity that the TBM can tackle. Because what if instead of having a linear model, for example, what if we had a decision tree working over those concept scores? Presumably the performance would improve with some trade-off with regards to interpretability. The modular nature of the TBM makes it so that you can sort of pick and decide where you want to lie in that interpretability versus performance spectrum. And one thing is that in this work, we focus on maximizing interpretability as much as we can. And even after doing that, we find that the performance is still quite decent, particularly for tasks involving sentiment classification. And I think that's the conclusion of this talk. Thanks to everyone for listening. Does anyone have any questions?
Thank you. Josh, I was just thinking about that some of these concepts are kind of vague, and even humans have trouble distinguishing them. Maybe you could spot those by, I don't know, asking GPT multiple times to classify a passage, and if you see a lot of variance in GPT's answers, then that suggests it's actually not a very clearly defined concept, and so maybe not one to include.
Yeah, I think that would work well too as a filter.
Peter?
I have a very interesting talk, Josh. I have a cost question that sort of scrolls all the way back to those first performance graphs that you showed, where you were showing, for example, your sentiment analysis task, where you show that fine-tuned GPT 3.5 performs about the same as your model, which I think has GPT 4 underneath. I was scrolling through your paper to find that. And then in the next, in your next task, you show that the fine-tuned GPT 3.5 is actually less or more performant than your model, which has GPT 4 underneath. Is so presumably a fine-tuned model, like a fine-tuned 3.5, costs way less than a 4 that you have to include that giant prompt in, right? So if 3.5 costs less and it's more performant, is it not doing the interpretability that you're getting out of the 4 model?
Yeah, there are really like the trade-off between doing fine-tuned GPT 3.5 versus using the TBM with GPT-4 is really like we trade a lot of things off in terms of performance and actually in terms of cost to get the interpretability benefits from the TBM, because the TBM actually costs quite a lot to run, because if you note, for each inference, we essentially have to run GPT-4 5 different times to arrive at our conclusion, because for each concept that we want to measure, we have to run an LLM, and we try to cut the cost down by batching some of the questions that we ask into a single prompt, but in the end it's still quite expensive, and that's something that we want to look into for the next work. And in our next work, actually, something we're looking into is that when we're generating these concepts, what if instead of the LLM generating a question that another LLM then answers, what if the LLM generates a piece of code to measure a given piece of concept? And we hope that by doing that, we can sort of cut down on the cost of running these text bottleneck models.
Thank you.
Josh, a related question here. I guess what would happen if you're doing concept extraction at the dataset level, so that's fine, that's a one-time cost. After you have a set of concepts, if you just provided them as a hint to GPT-4 that these are the kinds of things that are relevant and important, without this big individual question for each one, just say that take into account build quality and in the case of movies like plot and this and such, while you make the answer. Does that do anything useful?
Mm-hmm. That might provide benefits for the model in terms of helping it focus on the same things each time it runs inference. But the main issue potentially there is with faithfulness, because each time the model focuses on those concepts, you're not necessarily guaranteed the same weighing. Under the TBM, one nice thing is that the global reasoning is quite consistent. So each time you have a negative atmosphere, you're guaranteed that reduces the 5-star quality by 0.165. And each time you have good price, or each time you have good value for money, you increase the score by 0.2. So if we were to load all of these concepts into context, you're not necessarily guaranteed that the way that those concepts are weighed across each inference will be the same.
I mean, and another use case for this, beyond faithfulness, which is a fine thing to care about. But if you don't care about faithfulness, the one thing I care about is sort of usefulness to the end user. And so, for instance, if this is a system that reviews, scientific papers, oh yeah, your scientific paper, 8 out of 10. Not very useful, but if that's all I get from my fine-tuned GPT-3 model. But if I get this breakdown, and that could be done the way Ashish is saying, like, oh yeah, scored along these sort of concept dimensions, and then you get this report out that says, oh yeah, this is novel, but it is redundant, blah blah. It has this sort of breakdown, but in a way that I, as an end user, can sort of review and understand where does this 8 out of 10 come from. And in a way that I can sort of double check where it came from, then it's another way I would care about these concepts, other than just the sort of the faithfulness aspect of it. So that's just another sort of point of view of this work where it has a place and of relevance. So.
Yeah, I can imagine that working quite well, actually, because one assumption that we make with this work is that the concept weights are fixed for each inference. But it could entirely be possible that when you're weighing a paper that, like this aspect is much more important in this paper because of the specific topic that it's looking at compared to this aspect. So for example, having a paper with really extensive, fully formed analyses might be more important if you're looking at a more established domain compared to somewhere where the explorations are much more tentative.
Right. Yeah. So having these fixed weights can be a little bit of a hamstring in those cases. Yeah. Good point.
On the efficiency, so you have to apply every concept definition to every example in your data set. There might be optimization ways of reducing that, like just classify the problematic cases and put the other ones aside.
Yeah. Something else that the system can do is each time we perform an inference, we're measuring all of the concepts all at once. But as you can see here, noise level in this bottleneck is not a very important concept. One thing that we might be able to do is that we can try to figure out in which cases does noise level become important. Because if you notice that, okay, atmosphere is negative or positive or whatever it is, maybe it's more important to measure noise level when you already figured out that atmosphere is a relevant factor. So having sort of like a hierarchy of concepts might be another way to extend the work compared to just having them flat out like this.
Hey, Josh. I also have some work which is on similar lines. So we have our bottleneck in morality. So kind of along ethics, but just the data is more fine-grained and personalized. But the important part is we also were exploring first what concepts could be there for different data sets. And the one way of exploration we have tried is reinforcement learning. So we have a policy which is generating these possible concepts, bottleneck concepts, and then we have an end task which is sort of evaluating it, and then we're getting the feedback to change it, and that seems to be not performing bad, like it's performing better than the end-to-end. And the other is that, so that's one part, like we added RL to it. Did you have any plans like that, or did you try it?
We don't have any plans for RL at the moment.
Okay, so it never came up, sort of like I was just curious. Okay.
Yeah.
And
In
the
terms
other, okay, please go ahead.
Go ahead.
Yeah, you were saying in terms of what?
I was just curious where you might think RL could fit into the framework here.
Yeah, I think like the concept names that you have, like these explorations you're getting from GPT, you can learn that for every data, like you're doing it through a prompt, right? Essentially. So we compared doing it through prompt and doing it through RL. And well, while the RL is still on iteration number 55, maybe by the time it reaches 100, iteration, it might perform better. Right now, it's almost at the same level as GPT, but only slightly better. And we have yet to study interpretability of those concepts and so on. So we have not evaluated in detail. On a cursory look, they look quite good. The other thing is that our model has also learned sort of question specific. We have both versions, question specific concepts and domain specific concepts. Yeah, but it would be interesting to catch up offline, I guess. I can show you what we are doing.
Great, we're at time. Josh, thank you again for putting in the time, and super exciting, super interesting work. Very, very thought-provoking. Let's give Josh a round of applause again.